we were discussing the electro-optics of KDP crystal and anisotropic crystal, and we have seen that how this crystal can be configured for longitudinal mode of operation. We have seen that how this hub voltage thing can be designed for switching of the modulator. So, now we will continue this discussion with the transverse configuration, and in this transverse configuration we will see how this induced birefringence and the consequent phase retardation can be used to switch the modulator, and what will be the requirement of this hub voltage in this case. We will see that this improvement is substantial, is quite considerable, which will be many times more than the ones which we have seen in the case of isotropic crystals and anisotropic in the other modes. So, this then we will look at a very different aspect of this geometrical side of this modulator design consideration, how this modulator has to be designed to get a very good performance, whether from kilovolt we started off our switching voltage, that is hub voltage, we can bring it down to some tens of volt. Then we will look at this Gaussian beam and its diffraction through the crystal. Then for optimum performance of the crystal, what will be the geometrical design, geometrical aspect, that we will see with a bit of algebra, and then we will recalculate the hub voltage, the reduced hub voltage, to see that the performance has really improved by incorporating this geometrical aspect of the crystal to operate as a modulator. Okay. So, the transverse configuration of this KDP crystal, we will look at the retardation and modulation aspect of this under this configuration. So, in the what we have seen in the longitudinal configuration, the retardation is independent of the crystal's length, that we have seen, because you have V by L, which is to represent E z, and you have the length of the crystal L. So, this L and L cancels. As a result, the retardation, that is the phase retardation, phase delay, it does not involve the length of the crystal. It is only the voltage that is proportional, this retardation is proportional to the applied voltage. That is, it depends only on the externally applied voltage. Then also in this longitudinal configuration, we saw that voltage is to be applied along the length of the crystal, that is, the voltage is to be applied along the direction of the light propagation. So, that the voltage, that is the electric field, and the propagation directions are the same. This is a little troublesome in the sense that when you apply electric field, you have to use a pair of electrodes on the front face and at the back face, that is the input side and the output side of the crystal. These electrodes have to be transparent, because otherwise this, and it has to be transparent in the frequency, in the wavelength range of the light that will be modulated, that will be propagating through the crystal. So, this is a little inconvenient, but this is achieved by putting a transparent electrodes, usually titanium oxide, any transparent oxide which is transparent at this wavelength, or by making an annular hole at the input side, so that you can apply the electric field from the ring shaped electrodes, but the electric, that is the light, can propagate through the narrow hole which are fixed on the, which are kept on the electrodes on the either side, that is at the input side and at the output side. So, put together This is a small inconvenience from the design point of view in the longitudinal mode of operation, whereas in the transverse mode of operation this does not appear, because you apply the electric field from the transverse side, that is from sidewise. So, in transverse configuration voltage is applied in the transverse direction, electrodes do not obstruct the light beam. This is the advantage, this is something positive about this mode of operation, in addition to mathematical figure of merit, in addition to the performance of this from the design, from the fabrication point of view, this is the advantage. And then the retardation in this case is proportional to the applied voltage and is also to the length of the crystal. This we have seen in our repeated discussions in several occasions, that when you operate in the transverse mode, then the phase delay is proportional to the applied voltage as well as the length of the crystal. When you apply when you put in the configuration transverse mode of operation, and this hub voltage is also proportional to the ratio of the width to length. We have seen in the last discussion also, it depends on the ratio of the length and width. So, this is one very useful aspect to design the modulator. By very suitably, by precisely designing this in terms of the width and length, you can reduce the hub voltage as well as you can optimize the performance, you can maximize the modulator performance. So, this ratio can be adjusted to tune the hub voltage, we will see that particular aspect as well. Okay. So, this is the transverse configuration, we have been repeatedly discussing on this. Your this is your Z polarization. In this case, look at this, now your orientation is like this is your Z direction and I apply the field along the Z direction. So, that in the ellipsoid only E z terms will be there in the index ellipsoid of the electro-optic crystal. So, E z is now being applied and that results in E x dash and E y dash. So, these are the two new principal refractive indices. This is the old y axis, this is the old x axis in absence of any external field, but the moment you apply the voltage, it is only this direction and this direction, you get the refractive indices, which are these are the new eigen axes in which the refractive indices are proportional to the applied voltage. And you put this, so you have an input polarization which is halfway through z and x dash. Z and z dash are the same in any case, because we have seen that when you apply this electric field along z direction, then it undergoes a rotation about this z axis, but z axis does not get disturbed. So, z and z primes are same, therefore, you apply the polarization which is halfway through z, z prime and x prime. So, that light is now launched into the crystal. We will see that this compensator, which is a bayonet Salil compensator, which provides the necessary optical biasing to shift the operating point at the desired position. So, that you get a linearity in the modulated light, and you have an analyzer which is at crossed position with the input. So, this is all by now it is known, and you apply the modulating voltage across the crystal in the z direction. So, that you get the electric field active across this z direction. Okay. So, this is the configuration. Incident light is polarized along 45 degree to x prime in the x z plane. I just now have explained that 45 degree to x z plane. So, halfway through your x dash and z dash. So, that is the incident polarization. In the crystal, light propagates along the y direction only. It propagates only along the y direction. You see this. So, this is your actually it is the y dash direction, because after this is your x, this is your y, this is your x dash, this is your y dash. So, in the y dash direction, the crystal within the crystal the light propagates along the new principal axis, eigen axis, that is the y dash axis. So, light propagates along this is important. Now, the polarizer and analyzers are at crossed positions. A compensator is placed before the analyzer to provide optical bias to push the modulator operate in the linear region of transmission. So, voltage versus transmission is in the linear region, which is achieved by this. We have seen in the earlier discussion how it can be pushed. Right. Now, now you have without electric field n x dash equal to n 0, n z equal to this. So, because now these are the two polarizations which are now coming into play. It is not y, because y is now the direction of propagation of light perpendicular to that y direction, y prime direction, y dash direction is the n x dash polarization and n z dash the refractive indices of the polarization. So, polarization parallel to x y plane sees refractive index n 0, that is why it is n 0 and it is n e. Now, with the field you have seen that it is because of this external field E z, your n x dash is modified with this the incorporation of this quantity which has come from the diagonalization or the axis rotation of the crystal. So, you get n x dash, which is the new principal axis refractive index, is equal to this, but n z dash it remains n z n e extraordinary light refractive index. So, it does not undergo any change. Therefore, the birefringence in this case is n o minus n e, which is the birefringence in absence of, even if we do not apply any voltage, the two lights will see the birefringence which is equal to this, because one is now this time along z axis your refractive index seen by the polarization will be n e, and along your x axis the refractive index x dash axis refractive index seen will be n 0. So, this is in absence of any field, this is the fixed birefringence which gives you that the different kind of quarter wave plate, half wave plate by adjusting the length of this birefringence in interaction, and this is the part which is because of the voltage. So, this is voltage dependent birefringence and this is the fixed one, and this requires the compensation. Okay. So, after travelling a length L in the crystal, the emerging field component along the x direction will be equal to y dash equal to L at this point a by root 2, because you have taken halfway through. So, this is coming because of the 45-degree inclination of the polarization with the z and x axis, and this we have seen that this is the fixed phase of this light and omega t is the time dependent phase, whereas this is the phase which is proportional to the external field. So, this part of the phase which has come into play because of the application of the external voltage. The emergent field component along the z axis, z direction, then will be equal to this, because in this case there is no voltage dependent phase which is coming into play. You may recall that this z dash does not involve any voltage dependent phase. So, it is only because of the x dependent phase that the change in the phase, that is the birefringence is change in the birefringence is only accounted for the presence of this quantity, this term which involves the external voltage. So, it is an external voltage dependent birefringence that involves, that is only due to the x dash polarized light, not because of the z polarized light. It does not undergo any change. So, that is pretty useful, that now E x dash has this phase, E z at the output of the crystal has this phase. This is the fixed phase which is carried by the z polarized light along the length of the lens. So, when at the output of the crystal it has this phase. So, these are the two phases of the two orthogonal polarized light. So, now we will have to take the superposition of this along the path axis of the analyzer. So, the phase retardation between the two linearly polarized light will be gamma is equal to this just difference of these two phases. If I take the difference omega t cancels, this will give you k 0 n o minus n e, difference of n o and n e into L, and this will be staying back as it is, and this is the only voltage dependent phase field dependent phase birefringence. So, I get this phase which is equal to this, as I have mentioned, this is the fixed phase which is staying back just because of the refractive indices of ordinary and extraordinary light without any electric field, and this is the phase. So, hence the phase shift induced by the applied voltage is this. This is the phase shift, only this quantity. This is not changing, this is the base phase, this is the fixed phase DC phase, this is the phase which is oscillating, which is changing with the voltage. Therefore, the phase shift induced in absence of the applied voltage is this quantity, which is the fixed phase. I have already discussed about this. This does not play any role in the modulation, it is only the constant phase that is staying. Now, in the case of modulator half voltage, in this case will be defined as the sum of these two pi and this, because anyway this is not playing. So, switching should be done only because of this voltage. So, you can write that pi equal to this. So, half voltage in this case will be equal to, and anyway this V by D has come for this electric field E z. So, V by D, because this is the transverse mode of operation, and V by D this represents the electric field. So, electric field into L, the length of interaction of the two travel of the two polarized light. So, that gives you the phase of the light, that is. So, therefore, you get a V pi, the half voltage in this case, which is equal to lambda by n 0 r 63 and is proportional to the width of the crystal and also the length of the inversely proportional to the length of the crystal. We have seen, we have given some special observation on this, that how this D by L can drastically change the half voltage, that the performance of the modulator very good by suitably designing this. We will see that more. So, in the transverse configuration, the half voltage is not independent of the modulator L, but it depends on the width to length ratio D by L. So, if we choose this factor, this we have seen that D by L, this factor if you choose appropriately, then the half voltage can be reduced drastically. So, operation at linear region, for that purpose you require again the modulator to operate, to bias at the 50% operating point, that is the same as one has to do in the case of longitudinal configuration. The same way that you have to insert a half wave plate, a quarter wave plate to create a phase difference of pi by 2 between the two polarized light. So, that the phase difference, the base phase can be cancelled. Commercial electro-optic modulator, this is taken from this site. This is an amplitude modulator electro-optic crystal using KDP. They are commercially available, but usually they are highly deuterated and operated with only low driving voltage, that is about 275 volt. You can see that the very drastic improvement. We started with some kilovolt of switching voltage, but this time it has only few hundreds of voltage. The design is cylindrical of diameter this, and the useful bandwidth is this. So, this is the one which are available in the in the market, commercially available and used in the signal processing, in the laboratory and in communications, light wave communication modulation systems. Now, we will look at this important aspect of this design of the modulator in terms of the geometrical parameters dimensions. You see that electro-optic modulators can be operated in the transverse mode when the hub voltage is proportional to. This is the key point of this discussion for this designing, which will give a very high boost, very big improvement in the performance of the modulator. D by L, this ratio can be suitably adjusted. Of course, it has to be reduced, can be suitably adjusted to bring down the hub voltage. In the analysis, we assume that D and L to be independent of one another. So, all throughout our discussion, we have not talked about D and L. We assumed some value of D, or we just kept it as it is. But if there is a relation between D and L, when you look at the design of the modulator, that is that will be limited by the diffraction. This will come from the relationship will come for optimum performance, of course, come from the diffraction of the light beam within the crystal. So, that part we are now going to discuss, and this is very useful in terms of this modulator design and can be applied for such crystal modulator designing. So, the minimum value of D is determined from the diffraction of the beam within the crystal. We will see that configuration. So, let us consider a Gaussian beam through the crystal. Usually laser lights are sort of Gaussian beam. So, at z equal to 0, it is not at z equal to 0, actually it is at the center of the beam, where the beam size is the minimum, that is what we call the beam west, that is the spot size, which is equal to W 0, and at a distance z 0 within the crystal. So, they are related. How this is the diffraction of the Gaussian beam. So, the spot size at a distance, let me see the figure. You see, you have this beam west here, which is W 0, and as you move away from this, the beam diverges. So, at any point which is z distance away from this west of the beam, then this is your W z. So, this W of z, the spot size at a distance z from the west, and the spot size at this point W, they are related by this equation. This is simply from the diffraction of a Gaussian beam. So, this expression can be very quickly derived from that expression. So, and this is the notation that we have used. Lambda dash is for lambda 0 by n, where lambda dash is the free space, because the wave is travelling within the crystal. So, the wavelength will be different, and so now because you do not want that the light should be out from the crystal, but you can maximize the light within the crystal. So, that is the design. So, the most part of the light which is travelling through the crystal will be within the crystal, and you can also and also that because you have to apply a voltage in the transverse direction, you will not allow unnecessarily the width to be more. So, that you lose a part of the width which is not being occupied by the beam. That means, the beam size and the width should be just hand to mouth, just it should be fitting each other, and there is no extra width, because putting an extra width will just require more voltage to get the same amount of field. So, that is the philosophy of this designing. So, by doing that, what we can see that when z equal to L by 2, that is half the distance of this is your L. So, half the distance at L equal to, and this is z equal to 0, where the beam is the minimum size west. At z equal to 0, the width and the beam size, they should be equal. So, d z equal to L by 2, this is, you just plug in this expression z equal to L by 2. So, you will get this value, very straightforward and very simple. So, then d, because now twice the W, you look at this I have called W at L by 2, twice of this will be d. So, that is the requirement. So, d equal to twice of W equal to 2 W 0 and this quantity. Now, I have to minimize this value of d for this d W, because this is the thing which is given, this spot size at the beam waist, but this is a function of the distance of the travel, that is because of the divergence. So, this is with respect to the spot size, how much divergence I can allow, so that it will just encroach this width of the modulator d. So, that is the philosophy. If I do that, then dw is equal to 0. This is the minimization of d. So, putting this left hand side, that is this equal to 0, I just differentiate this quantity, which will lead to this again a very basic differentiation, which will lead to this expression. And if I use this expression, we can find out, because from here we will get the value of W 0 in terms of lambda dash L. So, that this lambda dash L, these values are going to decide what will be the W 0. So, that you get this minimum value of d. So, to get the minimum value of d, what will be the value of W 0, that I find out from this algebra, which is equal to your W 0 under root of lambda prime L by twice pi. So, this is the quantity, this should be the beam waist. So, beam waist and the length of the crystal, of course, the wavelength is there, beam waist and the length of the crystal, they are related in this way. And if I know that, then I also know, because this value I can plug in to this expression. Now, that I know the value of W 0, I know the value of W 0. So, this value of W 0, which will come from here, will be plugged into this expression, which will in turn give me the value of d. So, this d value is the optimum value, the exact critical value. We can give some more tolerance to this, because if we just put it, then there is a chance of, it requires a very high precision alignment and should be extremely stable, that is also the second requirement. But if you give a small tolerance to this, so this is the exact critical analytical value of d that is required when the L is given. So, d and L, they are now geometrically related through the Gaussian beam diffraction optics. Now, in practice there will be a tolerance. Just now what I said, that if it is exactly this value in terms of this, then it will be a very alignment critical operation, and also it has to be extremely stable, because otherwise any small fluctuation in the positioning will miss out the beam outside the crystal. So, there is a small tolerance. This factor is, tolerance factor is between 3 to 6 for practical design. This is all experimental values which are found out, and so in that case there is a factor S which gets into this 2 S and this. So, this is the design for this. Now, we will see, after having this design, that is when this d and L values are related through this parameter, then what is the half voltage. You can see very interesting, that let us assume a typical crystal length of 2 centimeter, which will decide the value of d through this calculation. Through this calculation, this will decide the value. S you have taken 3, because it can be well within 3 to 6. So, if you take the minimum value of 3, then this is the value of d. Now, a laser operated at this wavelength, helium neon gas laser at this operating wavelength, I assume that wavelength lambda 0, refractive index of this KDP, ordinary refractive index 1.512, if you assume, these are the values that if I use in this expression, I can calculate the value of d, which will be some fraction of millimeter. So, d on this calculation, it gives you 0.035 millimeter, which is a very thin width of the crystal. So, now if I use this d value in the V pi, that is your half voltage, that lambda L is 2 centimeter. We have already assumed that L equal to 2 centimeter, which has given me a d value which is 0.038 millimeter. Of course, you have already included the tolerance factor 3, otherwise it would have been 3 times less. Even if you round it up to 0.04 millimeter, 1/100th of a millimeter, which is very thin, in that case for 2 centimeter of crystal with a thin width, you get that the after this you get an operating a V pi which is about 300, and which is the line voltage 314 volt, which is now drastically very small. You can see this is about 1/125 times less than the V voltage which was required in the case of longitudinal mode of operation. So, there has been a tremendous improvement from kilovolt to volt, from tens of kilovolt to some hundreds of volts. There has been a tremendous improvement in the switching voltage just by taking the geometrical consideration of this design. This is how L and D are related through the spot size at the waist, that is W 0. So, this design is very useful for this crystal modulator designing, and then you see that this hub voltage has been reduced drastically. So, this is how we have understood that you can actually have the freedom of designing the crystal. In the case of transverse configuration, when you evaluate this induced birefringence and then phase retardation, you end up with a hub voltage which is large reasonably, but once you incorporate this geometrical aspects of the modulator in terms of the length and width of the modulator, such that most part of the light beam which is travelling through the crystal is utilized by the modulator, by the electric field. Also, you do not allow any excess of width, such that unnecessarily the voltage requirement becomes more in order to get the same electric field. We also discussed this Gaussian beam diffraction result for getting the optimum performance, and we saw that the reduced hub voltage which is of the order of some 300 volt. We will continue with this discussion. Thank you very much.